Burn a book, the book is destroyed. The pages turn to ash. The words disappear. The information, every letter, every sentence, every idea seems gone forever, erased from existence. But it's not gone. Not really, not according to the laws of physics. The smoke particles carry information about the molecular structure of the paper. The heat radiation encodes details about the combustion process. The ash contains traces of the ink patterns. The photons emitted carry away data about the chemical composition. Every single piece of information about that book still exists, scattered across billions of particles, dispersed into the environment in a form so scrambled that no practical measurement could ever reconstruct it. But in principle, given perfect knowledge of every particle's position and momentum after the burning, you could run the physics backward and figure out exactly what the book said. The universe keeps records, perfect records, of everything that has ever happened. I'm Leonard Susskind, and I'm going to explain why the universe has a memory, why information is never truly destroyed, why every event that occurs leaves an indelible mark on the quantum state of the cosmos, why the past is not erased but encoded permanently in the structure of reality. This is not metaphor, this is physics, and it's one of the most profound principles we've discovered. Let me show you why. Start with classical physics. Newton's laws are time reversible. If you film particles bouncing around and play the film backward, the reversed motion obeys the same laws as the forward motion. Every collision, every interaction works equally well in reverse. This means the future is determined by the present, and the present is determined by the past. But it also means something deeper. The past is encoded in the present. If you know the exact state now, every position, every velocity, you can calculate the state at any earlier time. The present contains the past. In principle, nothing is forgotten. The entire history of the system is encoded in its current state. This is Laplace's demon again. A hypothetical intelligence with perfect knowledge of the present could reconstruct the entire past. Every event that led to the current state would be calculable. The universe has a memory, and that memory is complete. Of course, practically, this is impossible. Tiny uncertainties grow exponentially. Chaotic systems amplify differences. We can't measure with infinite precision, so reconstruction fails quickly. But the principle stands. The information is there, scrambled beyond recovery, perhaps, but not destroyed. Now move to quantum mechanics. And this is where the principle becomes absolute. In quantum mechanics, information is conserved by unitarity. The quantum state evolves according to the Schrödinger equation, which is unitary. Unitary evolution preserves information completely. You can always run it backward. The future determines the past just as surely as the past determines the future. This is stronger than classical mechanics. Classical mechanics says information is preserved if you know everything perfectly. Quantum mechanics says information is preserved, period. It's a fundamental law. The total information content of a closed quantum system never decreases. You can scramble information, you can spread it out, you can make it practically inaccessible, but you cannot destroy it. This is unitarity, and it's one of the foundational principles of quantum mechanics. Every experiment we've ever done confirms it. The quantum state evolves reversibly, information is conserved. Now here's where it gets philosophically profound. If information is never destroyed, then the past never disappears. Everything that has happened remains encoded in the quantum state of the universe. The Big Bang, the formation of the first stars, the evolution of galaxies, the development of life on Earth, every moment of your life, from birth to this instant, all of it is recorded in the quantum state of every particle, every field, every degree of freedom in the cosmos. The universe is its own archive, a perfect, comprehensive, permanent record of its entire history. You can't access most of this information. It's scrambled into correlations between distant particles, encoded in entanglement patterns too complex to measure, but it's there. The past exists as information distributed across the present state of everything. Now let me tell you about black holes, because this is where the memory of the universe becomes most dramatic and most mysterious. When you throw something into a black hole, it crosses the event horizon and falls toward the singularity. From the outside, it's gone. You can't retrieve it. You can't see what happened to it. The information it carried has disappeared behind the horizon. But has the information been destroyed? For decades, this was an open question. Stephen Hawking argued, yes, black holes destroy information. When the black hole evaporates via Hawking radiation, the information is lost. Unitarity is violated. I argued no information must be preserved. It can't be destroyed. The Hawking radiation must somehow encode everything that fell in, even if we don't yet understand how. This was the black hole information paradox, and it was finally resolved in favor of information conservation. The universe keeps records even of what falls into black holes. How? Through the holographic principle. The holographic principle says the information content of any region of space is proportional to the area of its boundary, not its volume. All the information inside a black hole is encoded on its event horizon. When the black hole evaporates, the Hawking radiation carries away that information, encoded in subtle correlations between photons emitted over billions of years. The radiation looks thermal random at first glance, but hidden in the correlations, in the quantum entanglement between early and late radiation, is the complete record of everything that fell in. Every atom, every photon, every bit of information, the black hole remembers, and when it's gone, the universe still remembers what was inside it. This is black hole complementarity. The idea that information is both inside the black hole and encoded on the horizon simultaneously, depending on your perspective. For an outside observer, the information lives on the horizon and is gradually released in the radiation. For someone falling in, the information crosses the horizon and heads toward the singularity. Both perspectives are valid. Both are complete, and both preserve information. Now let me make this concrete with an example. Suppose you write a message and throw it into a black hole. The paper crosses the horizon. From your perspective outside, it's gone. But the black hole gained mass, a tiny amount corresponding to the mass energy of the paper. The horizon area increased slightly, and encoded in that area, increase in the pattern of quantum correlations on the horizon is the complete information about your message. Over trillions of years, the black hole evaporates, the Hawking radiation carries away that information. Not in any obvious form, you can't read the message by catching individual photons, but the information is there, distributed across the radiation's quantum state. In principle, if you collected all the Hawking radiation and had unlimited computational power, you could reconstruct the message perfectly. The universe didn't forget. It encoded the information and preserved it through the black hole's entire evaporation. Now let me tell you about the cosmological horizon, because this raises an even stranger question about memory. In an expanding universe, there's a cosmological horizon. Light from beyond a certain distance hasn't had time to reach us yet. Those distant regions are causally disconnected. We can't see them. We can't interact with them. Does the universe remember what's happening beyond our horizon? The answer depends on what you mean by the universe. If you mean our observable universe, the region we can see and interact with, then no. Information beyond the horizon is inaccessible to us. It might as well not exist from our perspective, but if you mean the universe as a whole, all of space-time, then yes, the information exists. It's encoded in the quantum state of those distant regions. The fact that we can't access it doesn't mean it's not there. This raises a deep question. Is inaccessible information still information? If a record exists but can never be read, does it count? Physically, yes. The quantum state exists, the information is encoded, unitarity is preserved. The fact that we're causally disconnected doesn't change that. Philosophically, it's murkier. If information can never affect us, does it matter? Is there a meaningful sense in which it exists for us? I don't have a definitive answer. But the physics is clear. Information is conserved globally, even if it's not accessible locally. Now, let me tell you about quantum entanglement and memory, because entanglement is how the universe stores information. When two particles interact, they become entangled. Their quantum states are correlated in ways that can't be described independently. Measuring one particle gives you information about the other, no matter how far apart they are. This entanglement is a record, a memory of the interaction. The fact that the particles are correlated means information about their shared past is encoded in their joint state. And this happens everywhere, constantly. Every particle that has ever interacted with another particle is entangled with it. The universe is a vast web of quantum correlations, encoding the entire history of every interaction that has ever occurred. Your body contains atoms that were once in stars. Those atoms are entangled with particles scattered across the galaxy. The light hitting your eyes right now originated in the sun's core, and those photons are entangled with the atoms that emitted them. Every breath you take involves molecules that have interacted with countless other molecules throughout Earth's history. You are embedded in a quantum web of correlations that extends across space and time. Your current state encodes information about all the interactions that led to you. The universe remembers by entangling everything. Now, let me address decoherence, because decoherence seems to destroy information. When a quantum system interacts with its environment, the superposition decoheres. The interference pattern disappears. The system appears classical. Does decoherence destroy information? No, it spreads information. The system's quantum state becomes entangled with the environment. The information isn't destroyed, it's diluted across billions of environmental degrees of freedom. In principle, if you tracked every particle in the environment, you could reconstruct the original quantum state. The information is preserved. It's just no longer localized in the system you're observing. This is why quantum computers are hard to build. Decoherence spreads quantum information into the environment, making it look like information loss. But it's not. The information is escaping, leaking out, being recorded by the surroundings. The environment is the universe's memory bank. Let me tell you about the no-hiding theorem. This is a mathematical proof that information cannot be hidden, even in principle. Quantum mechanics allows information to be scrambled. You can take a quantum state and spread it out across many particles through entanglement. You can make it practically impossible to recover. But the no-hiding theorem says you can't make information disappear completely. If information seems to vanish from a quantum system, say, through decoherence, it must appear somewhere else, either in another quantum system or in correlations between systems. The total information is conserved. It can't hide, it can't be destroyed, it has to go somewhere. This was proven mathematically by Samuel Bronstein and Arun Pati in 2007, and it's a direct consequence of unitarity. If quantum evolution is unitary, if it preserves information, then you cannot have a process that destroys information. The information has to be traceable somewhere in the final state. This applies to black holes. Information can't hide inside. If it's not in the radiation, it must be somewhere on the horizon, in correlations, in subtle quantum states we haven't measured yet, but it must be somewhere. The no-hiding theorem guarantees the universe keeps records. Information cannot be erased, only redistributed. Now let me tell you about quantum error correction, because this is how the universe protects its memory. Quantum information is fragile, decoherence destroys it, Interactions scramble it, noise corrupts it, yet somehow quantum correlations persist. Entanglement survives. Information is preserved even as individual particles interact chaotically with environments. How? Through redundancy, through quantum error correction codes built into the structure of space-time itself. In quantum computing, we protect information by encoding it redundantly across multiple qubits. If one qubit decoheres, the information can be recovered from the others. The code is fault-tolerant. The universe does something similar. Information about an event is encoded redundantly across many particles. No single particle contains the complete record, but collectively, the correlations preserve it. This is how black hole information survives. It's not in any single photon of Hawking radiation. It's in the collective quantum state of all the radiation. The code is spread across the entire evaporation history. The universe has built-in error correction. Information is so robustly encoded that even violent processes, even black hole evaporation, can't destroy it. Now let me tell you about something that deeply bothers me. The cosmological constant problem. The vacuum has energy. Dark energy, about 10 negative 9 joules per cubic meter. This energy drives the accelerated expansion of the universe. And its constant in time doesn't dilute as the universe expands. Where does this energy come from? Quantum field theory predicts vacuum energy from quantum fluctuations, but the predicted value is 10^122 times larger than observed. This is the worst prediction in physics. Something is wrong. Either our calculation is wrong, or something is canceling most of the vacuum energy, or the vacuum energy doesn't gravitate the way we think. But here's what bothers me about memory. If information is conserved and the universe is expanding, where is the information about the initial state stored? If the universe started in a low entropy Big Bang and is now in a much higher entropy state, where did all that information about the high entropy state come from? The second law says entropy increases. More microstates become accessible over time. But if information is conserved, how can the number of microstates grow? It seems contradictory. The resolution involves the cosmological horizon. In an expanding universe, the number of degrees of freedom within the horizon changes. The horizon grows, encompassing more volume, more information. The accessible Hilbert space, the space of quantum states, expands. Information is conserved, but the available memory capacity grows. The universe can encode more information over time because it's getting bigger. This is subtle and not fully understood. Cosmology and quantum information theory don't mesh perfectly yet. We're still working out the details. But the principle stands. Information is conserved. The universe remembers. Let me end with the practical impossibility and the theoretical certainty. Practically, the past is inaccessible. You can't unburn a book. You can't unbreak an egg. You can't reconstruct your childhood from the current positions of atoms in your body. The information is too scrambled. The measurements would need to be too precise. Chaos amplifies small errors exponentially. But theoretically, the past is encoded in the present, completely, perfectly, reversibly. Given infinite measurement precision and infinite computational power, you could calculate backward through time and reconstruct every event that led to now. The universe is deterministic in both directions. Past determines future. Future determines past. Neither can happen without the other. They're two sides of the same coin. And information, the pattern of bits, the structure of states, the correlations between particles is the currency connecting them. Information is conserved always, without exception. The universe never forgets. It can't. The laws of physics don't allow it. Every event leaves a trace. Every interaction creates correlations. Every moment adds to the permanent record encoded in the quantum state of everything. You are part of that record. Your existence is encoded in the structure of space-time, in the entanglement patterns of particles, in the correlations stretching back to the Big Bang. The universe remembers you, and it will remember you forever.